So today I'm going to talk about mapping with satellite data beyond the typical Landsat and Sentinel-2 that's pretty widespread. And mostly I'm going to be talking about using a tool called Gdal, which is a library for working with geospatial data on the command line. It's a lot. And so I have actually an entire series of blog posts that break it down from the very beginning. The URL is here from my Medium channel where these are, but it's also in the Slack. And then there's another one that's specifically for using Gdal to read NetCDF and HDF, along with sample files and more code and more examples of how things can break in weird and interesting ways. So there are literally thousands of data sets produced and archived by NASA, ESA, JAXA, other international space agencies, many of which are going to make completely fascinating maps. Everything from energy balance to forecast temperature, sea ice thickness, and rainfall. Unfortunately, these are often stored and distributed in data formats that can be difficult to read. Formats like NetCDF, HDF, and GRIB. And these types of data have two qualities that sort of make them so hard. They're extremely flexible, and they're inherently multidimensional. And so the flexibility means that you can store many, many different types of data in a single file. And it doesn't even have to share the same dimensions or data type or anything. It's just a complete Wild West out there. And then they're also multidimensional, which means not only can a single file have many different parameters, but they could be different time steps or even different levels. So think elevations for air temperature data set that go from the surface to the top of the troposphere. And so they're just inherently complex data, which is great for a data provider, but not so great for somebody who just wants to pull a single data set out. Before I get into Gdal, I will point out that there are some GUI-focused tools that will work with HDF, NetCDF, et cetera. QGIS, one thing to note is that you will need to specify the subdata set or the parameter when you're pulling it into QGIS. And then ArcGIS Pro also has support for multidimensional data. One caveat is there are still ways for this data to be broken, especially how the georeferencing works, and you're going to need to fix that as a separate step anyways, and often the easiest way to do that is going to be Gdal, despite all of its faults. And then there's a tool called Panoply provided by NASA. This is actually great at interpreting all of that geolocation info. Unfortunately, it requires Java, so if you're in a professional environment, your sysadmin might not let you install that. And also won't let you export GeoTIFF, so you're stuck with the mapping capabilities within Panoply itself. Now, if you're going to get started with Gdal, you need to install it. That in and of itself is a complex thing. If this is all impenetrable to you, please reach out to me on Slack or come up to me and I can actually walk you through how to do this. I recommend using an environment manager or a package manager called Miniconda. Create an environment specifically for working with Gdal, tie it to the CondaForge channel, and then you need to install Gdal, and you need to install the libraries to work with the scientific data formats. Again, don't expect you to memorize this, but please come up and ask me how to do this. Now, approaching scientific data is a lot like solving a puzzle, because each of these files can be completely different from the other files that you might have been exposed to. And so what I recommend is sort of developing a workflow rather than trying to have a simple recipe that's just following these steps. First part of that is to read the metadata to find the file structure, and Gdal info is your friend there. Parse the data with a function called Gdal translate, and then you may have to reformat the data for additional analysis and visualization with Gdal warp. And I'll start with a relatively simple data set, sea surface temperature. This particular file has multiple parameters, but only a single time step. However, it does have incomplete georeferencing, which I'll show you how to fix. So first step, read metadata with Gdal info. And it's type in Gdal info, and then probably copy and paste in the file name, since they can be long. You'll notice with this particular file, it ends with a .nc, and that stands for NetCDF. And it spits out a bunch of text, and what you want to be focused on is these sub-data sets, at least at first. Hopefully that's big enough to read. And so there are 4 different parameters in a single file. There's the sea surface temperature itself, there's an error bar, there's a mask to distinguish good from bad data, and then sea ice fraction for near the poles. And we want the sea surface temperature data, and so we want to pull out this first subdata set. And you'll notice that it says subdataset _1 name equals. Everything after the equals sign is the name of that subdata set. So it's like all of the quotes, all of the colons, all of the stuff you normally don't put into a file name, but you need to include it. And so we go back to Gdal info, and now we point it to that subdata set itself. And again, it spits out text even more this time, and I'll just walk you through some of the more important parts. So first, it tells you the file's dimensions. Here it's 7200 by 3600 pixels. Looks like it should be a nice lat-long projection. And it actually even gives you the origin and the pixel size. But you'll notice that these aren't nice round numbers, which should throw up a little bit of a red flag. And I'll address how to fix that in a little bit. And then it also shows you some information about the data itself. In this case, it's float 32, so it's a 32-bit data set. It's not the type of nice integers that we usually display as a grayscale or combine into true color. No data is assigned a not a number value, and then the unit types are kelvins, not degrees C, which is a good thing to know because they're unusual relative to Celsius or Fahrenheit. Next step, parse the data. And here we use a new tool, Gdal _translate, and here you give it the subdata set name and then the output file. And again, it's that subdata set name is that whole long string, messy characters and all. And then you give it an output name. And here I've simplified it and added .tiff. Gdal is really nice in that it will automatically try to parse your file extension. And so this command will write a geotiff. Unfortunately, what it's doing is it's just pulling that floating point data out of the scientific format and writing as a geotiff. It's not doing any additional scaling. So we actually need to specify that if we want to make an image for display. So returning to Gdal info, run it on the TIFF just created, and then add the -mm flag, which stands for min-max. And then if you do that, you'll actually see that there's this line that says computed min-max. And so that's giving you the minimum and maximum values in kelvins. Now, to make that into an image, we need to scale those floating point values into a single byte, which is going to range from 0 to 255 and give you 256 grayscale levels. And you do that with the scale flag. It's -scale, input min, input max, output min, output max. You know, I'm intentionally setting this to bytes, so the output min and output max are 0 to 255, and you are usually going to set that to the max extents of the output data type. And then you'll also notice I added a -ot byte flag, and this is going to specify that the file is a byte file and not just rewriting another floating point file. And then you get a nice grayscale image in a Poincare projection. However, if you try to do anything more complicated than overlay a continental outline, this will break. If you try to reproject it in QGIS, it won't even give you an error message. It just won't do it, which is a little bit frustrating. And to do that, we need to go back to that initial info we got that gave you these wonky origin and pixel size. So something in the file, I don't actually know what it is a little bit wrong. And Gdal and QGIS are not interpreting it properly. And so I can guess 7200 by 3600 pixels is probably 0.5 by, or 0.05 by 0.05 degrees. But to double check, I actually went back to the dataset documentation published on the web, and sure enough, -90, 90, -180, 180. Now, there's two approaches to fix that. You can either use Gdal translate to assign a new spatial reference system, or you can use Gdal warp when you're doing the reprojection to tell the reprojection software what the initial reference system is, and then tell it the target reference system. And with Gdal translate, you kind of do that at the first step when you're pulling the data out. And so -a, -assign, _SRS, spatial reference system, our old friend EPSG 4326. I assume most people here know what that means. And then I'm specifically assigning what the upper left and lower right pixels are to make sure that they are the right rounded numbers. So -a assign, UL, LR, upper left, lower right, -180, 90, et cetera, et cetera. The other way to do it with Gdal warp is setting this source spatial reference system and then telling it it's EPSG 4326. And then the target spatial reference system is 8857. If you haven't memorized that, which you probably haven't, that's equal Earth. And so we have a nice equal area projection. You can add colors, you can add continental outlines, masks, all the stuff that makes a good map. Next example is going to be a more complicated, more multidimensional data set from an instrument called Ceres. This one not only has multiple parameters, but also has multiple time steps, in this case 12 months for each parameter, and then a different type of messed up unconventional georeferencing that needs to be fixed. Again, first step, read metadata with Gdal info. There's the command, and then I've highlighted the subdata set that I want to look at. In this case, it's called top of atmosphere net flux, although it is abbreviated. Parse the data. Again, Gdal translate, subdata set name, something.tiff. And then you pull it into QGIS, because I haven't done any conversion from floating point yet, and QGIS nicely does handle floating point data. And you'll notice that this looks a little weird. It doesn't really look like it's a single parameter that has a color palette applied to it. And that's because Gdal is handling those time steps as bands. So just like red, green, blue in a true color image, or band, short wave infrared, near infrared in a Landsat image, they're just a numbered sequence of bands. So in this case, January is 1, displayed as red. February is 2, displayed as green. March is 3, displayed as blue. And what we really want to do is pull each of those individual bands out. And you do that with the -B flag, which stands for band, and then specify the band. Notice it's one indexed, not zero indexed like Python. So March, month 3, and just -B3. I've also done some scaling, output the TIFF, and you get the nice grayscale expected with the single parameter. However, you may notice that this doesn't run from the international dateline to the international dateline from left to right. It starts at the prime meridian and runs 360 degrees. So it's mathematically perfectly valid, but mapping software is really going to struggle with this. And so what we need to do is we actually need to remap that data to be the conventional WGS84. And we do that in Gdal warp again because we're actually moving the data around. And you set the source reference system, long lat projection, specify the ellipsoid, but nothing about the input lat and long or the coordinates, corner coordinates, and then specify the target SRS, in this case back to EPSG 4326. And we need to be explicit about what we're setting the center longitude for. And so --config space center _ long 0. And then you get a properly georeferenced global data set. Since it's Gdal and it's running on the command line, we can batch process this and we can step through all 12 months and make a nice annual climatology of net flux or energy balance on the Earth. And so that shows you sort of the power of why doing this on the command line is really helpful, even though it's hard. So reading complex data is a process. You're not going to memorize specific ways to work with all of these different data sets. So really, the most important thing, learn to read and interpret the metadata, and then develop a library of techniques, and use those to fix some of the common problems that will crop up again and again and again. As I said, it's complex. I don't expect anybody to actually remember the syntax, and so please go to the blogs or approach me, and I'd be super happy to help out.
Give it up for Robert. All right. We have time for one very quick question. Yes.
It's possible that I've actually asked you this before, but you mentioned at the end that this is good for batch processing. How do you go about that, especially with like Gdal translate, where you have to manually put in the min and max values before you convert them?
So there's a bunch of different approaches. Probably the most straightforward is to use bash, which is scripting, the standard scripting language for Unix shells. And what you do is you can actually point it at Gdal info, and then use certain complex things that I don't fully understand, like regex, to just grab the part of the data, the output that you want, and then like put that into a variable and then run it.
Thanks.
All right, thank you, Robert. Please reach out to Robert separately if you have any more questions.